video I will present to you a solution to IMO Shortlist 2020 problem N2. Firstly, we take a look at the statement. For each prime p, construct a graph GP on the set of positive integers less than or equal to p, where m not equal to n are adjacent if and only if the following property holds. P must divide m squared minus n plus 1 times n squared minus n plus 1. We want to prove that GP is disconnected for infinitely many p. Before we begin, I'm going to make up a little bit of notation, so let GP equal to v comma e, where v is its set of vertices and e its set of edges. We want to think of what we know about connected and disconnected graphs. One thing that should come to mind is a tree. A tree is a graph with many different definitions, which are all equivalent, of course, because it's the same thing. And we have a list on that on our wiki, which we have linked in the description, as we always do with anything that we cite. So let's continue. A tree is a minimal connected graph. Therefore, this property fails if we remove any of its edges. This is interesting because we also know that any tree of p vertices has exactly p minus 1 edges. Therefore, if we could show that GP doesn't have enough edges, or to be exact, less than or equal to p minus 2 edges for infinitely many primes p, then we would be done immediately, because the number of edges would not be sufficient to be connected, because a minimal connected graph must have at least, or does have exactly p minus 1 edges. So I'm going to write that down. Enough magnitude of E less than or equal to p minus 2 for infinitely many p. Okay, this is also very nice because the magnitude of E is a very global property of the graph. We can evaluate it using many different strategies. If this approach were to fail, then there's not such an easy solution to just say there are not enough edges to connect all the vertices. Then we would have to make use of some kind of local structure of GP to prove the statement. But in this approach, we look at the magnitude of E, and one way to count it is using the handshaking lemma. I think you should not always call it that, because the statement is intuitive to prove, because if we sum up the degrees of all of the vertices, so the number of edges each vertex is incident on, and if we sum that up, then that's exactly twice the number of edges in this graph, because every edge is incident on 2 vertices. So it would be a good idea if we would find a way to evaluate the number of edges incident on each vertex n. M is adjacent to another vertex n if and only if n is congruent to m squared plus 1 mod p, or n squared plus 1 is congruent to m mod p. Okay, this is a condition, but not very nice yet, because even though this is entirely symmetric originally, from the point of view of p, we now have 2 cases, which are pretty different. In particular, this one is not that hard to evaluate. Just look at how many n's could fulfill this property. Well, there's exactly one residue class, namely m squared plus 1 mod p, and n must be exactly of this residue class. So pretty easy to evaluate. On the other hand, given an m, it is not that trivial to see how many n fulfill the property that n squared plus 1 is exactly in the residue class given by m. Therefore, we modify the approach a little bit and define a new graph, g prime of p, which is a kind of a directed version of GP. We maintain all of the edges, but label each of them with a direction. What do I mean by that? Well, E prime, the set of its directed edges, shall be the following subset of v squared. First of all, m of course must be not equal to n, but secondly, p divides m squared minus n plus 1. We can check that by this, we always also maintain all of the edges in E, because if this is true, then we get an edge going from M to N in G prime P. And if this is true, we get an edge which is just directed the other way around. Of course, it is possible that both conditions hold for M and N, but in this case we would only count the edge more times in E prime, which is not a problem because that's the correct direction. So we write down that the magnitude of E is less than or equal to the magnitude of E prime. This is good because we want to bound this quantity from above. Now we want to evaluate this quantity. This is nothing but the sum going over all vertices M of the number of outgoing edges from M in G prime P. Because then we would count every edge exactly once, because every edge has one vertex from which it comes out. So this is nothing but the sum of M in V of the magnitude of N in V, such that M is not equal to N and P divides M squared minus N plus 1. Of course, this set cannot have a size exceeding the value of 1, because there's only exactly one residue class equal to n squared plus 1, and for that we add a 1 to the set, 1n. But this set could also have size 0, and this is exactly the case if this residue class n is again equal to n. So first of all we write down that this is less than or equal to p, which is not quite enough, but since we know how to lower this sum, we can exactly determine what condition needs to be true in order to show this statement for a given p. In particular, we need to have two residue classes such that plugging in m for n gives p divides m squared minus n plus 1. And this is the exact condition which needs to be true for two different residue classes in mod p. I claim that one such solution already implies a second one, mod p, for almost all values of p, and therefore we could be able to replace this 2 with 1, but we have to prove that claim, of course. But it follows from the fact that we have a quadratic right here, and quadratics have a symmetry axis, as you know from the real numbers, and therefore this has a symmetry at x equals 1/2, and we get that m squared minus m plus 1 is equal to 1 minus m squared minus 1 minus m plus 1. Therefore, m works implies 1 minus m works. Very good, but m and 1 minus m could be equal modulo p, which would be a bad luck for us. We have to consider this case as well, so let's do that. If m is congruent to 1 minus n mod p, this is nothing but m is congruent to 1/2 mod p. I want to say two things about that. First of all, we need to require p is greater than 2 for this to work, because otherwise this doesn't have any solution at all and this doesn't exist. And the second remark is why this exists. When I was introduced to this notation, I found it irritating, although it should really make sense for modulo p, because 2 doesn't share a factor with p, and therefore for whatever we write on the top here, we can say that, okay, I'm going to define what does 1/2 mean. Well, it is just the residue class mod p, which does exist, and there's only one such residue class, such that 2 times m is congruent to 1. And this we just define as 1/2. So it all works out pretty nicely. But this implies that m squared minus m plus 1 is congruent to 1/4 minus 1/2 plus 1, so 3/4 mod p. And I want to note this all works because We are dealing with fractions with denominators that do not share factors with p. This is not congruent to 0 mod p, because again this is the residue class. If you multiply it with 4 you get 3 mod p, and obviously that can't be 0 unless 3 is also 0 mod p. So I'm going to restrict this right here with p greater than 0, and then this condition holds. So we have shown that if m is congruent to 1 minus m, then this can't be true. Therefore, if this is true, then these two values are different, but the other value also has the property that this divisibility holds, and therefore one solution always implies the second one, at least for p greater than 3. Therefore, we know that it is enough to find one solution for infinitely many primes. We are interested in showing that there exists infinitely many primes p greater than 3, such that for some integer m, p divides m squared minus m plus 1. To show that, we are going to present two proofs, one of which is elementary but employs an important strategy, and the other one is more technical, uses lots of theorems which are important to have seen. So let's get into the first solution. There exists a pretty standard proof for the existence of infinitely many primes. What we do is to assume that there are only finitely many. We multiply all of them and add 1. This new number is not divisible by any of these primes, which is a contradiction because it is larger than 1. We do something very similar in this case. So start with assuming the opposite. There are only finitely many such primes. I call them P1 to PR. Then we let M be their product. And then for all such indices I, Pi does not divide m squared minus m plus 1, but this number is of this type, and it is also larger than 1, because we can verify that at least one prime is in this set, because for instance, plugging in m equals to 3 yields p is 7. So 7 is in the set, so m is greater than or equal to 7, therefore this is definitely greater than 1. Since none of these primes divided, this is a contradiction. And we are done. Now we'll take a look at the second proof for why this is true. In this situation where we're looking at divisibility by p, it makes a lot of sense to consider our situation in the prime field Fp. We can think of that as a set of the numbers 0, 1 up to p minus 1, where those are not the natural numbers, but rather elements of Fp, and these are just labels for them, but they make a lot of sense, because now we can define addition and multiplication in this field, just as we would modulo p. And this is really nice, because we can use the result that if p is a prime, then this is actually a field. Therefore, division is well defined under this notion. Now, the question becomes whether there are infinitely many primes p such that this polynomial x squared minus x plus 1 has roots in Fp. Because we see that if we can find an element of Fp, x, such that this polynomial evaluated at x is equal to 0 in Fp, then the corresponding integer m must also satisfy this condition by the definition of Fp. So what do we do to find the roots of a polynomial? The normal approach for doing that is to find a factorization for it. And we know that in the complex numbers, all polynomials of this kind can be factorized into linear terms. In particular, in complex terms, x squared minus x plus 1 is equal to x minus 1 plus the square root of negative 3 over 2, multiplied with x minus 1 minus the square root of negative 3 all over 2. Now, this factorization might not immediately make sense in Fp, because the square root of -3 is definitely not an integer and not even defined within the real numbers. And therefore, it seems kind of surprising, it would be surprising if we were able to do that in FP. But the only property of the square root of -3 that we are using in this complex factorization is that this is a number where when we square it, then its value is equal to -3. And it seems quite possible that there exists an element of FP that such that if you square it, its value is equal to -3 or p minus 3 in FP. So basically, we have transformed our problem into a new one. We want to find out whether the equation x squared is equal to -3 has solutions in FP. Now, I really want to note that what we have done is to transform the problem of deciding whether this polynomial x squared minus x plus 1 has roots in FP to deciding whether another polynomial, namely x squared plus 3, has roots in FP. At first sight, it might seem like we have not made lots of progress, but there's actually much theory known about this kind of polynomial where there's no linear term. Because what we are actually looking after is, as I've written it down right here, to decide whether -3 is a quadratic residue modulo p. And there is a notation for that. We define the Legendre symbol, a over p, as 0 for p divides a, 1 for a quadratic residue mod p, and -1 if a is not a quadratic residue mod p. And therefore, by this definition, we only want to find infinitely many primes such that the Legendre symbol of -3 over p is equal to 1. And we want to prove that this relationship is true for infinitely many primes p. So we have reduced the problem again to finding infinitely many primes p greater than 3 such that the Legendre symbol of -3 over p is equal to 1. Another fact, which is known as Euler's criterion, is that the Legendre symbol of a and p is congruent to a to the power of p minus 1 over 2 mod p. This we will use multiple times because now we can compute -3 over p using another statement, of course, because firstly we notice that because of Euler's criterion the Legendre symbol is multiplicative in its top argument because a times b over p is a to the power of p minus 1 over 2 times b to the power of p minus 1 over 2, which is a over p times b over p. Thus, -3 over p is -1 over p times, of course, +3 over p. And now we will use another statement known as the law of quadratic reciprocity. Firstly, this is equal to -1 to the power of p minus 1 over 2 times, by quadratic reciprocity, p over 3, which is exactly the inverse of that, because this works because 3 is also a prime and p is not equal to 3 because p is greater than 3, times -1 to the p minus 1 over 2 times 3 minus 1 over 2. We note that 3 minus 1 over 2 is equal to 1, therefore this cancels, and we have -1 to something times -1 to the same thing, and therefore those two also cancel, and we are finally left with p over 3. Let's take a look at the definition of the Legendre symbol again. We see that p over 3, so in this case these two will switch roles. So okay, p over 3, of course it's never 0 because we consider large primes and then 3 does not divide p, so we are only left with these two cases. And p over 3 is 1 if p is a quadratic residue mod 3. But we also know that the only non-trivial quadratic residue mod 3 is 1, because 1 squared is 1 mod 3 and 2 squared is also 1 mod 3. Thus, this is equal to 1 if and only if p 2, 1, mod 3. But now we know that by Dirichlet's theorem on primes in arithmetic progressions, there are infinitely many such primes because 1 and 3 are both co-prime integers. Therefore, there exists infinitely many such primes, for which also this condition holds, and therefore there exists also an m for them such that p divides m squared minus m plus 1. Therefore, we are done.